Good morning, everyone. We're going to continue this morning in chapter 5, and we're starting kind of a new section today on calorimetry, which is the study of heat changes that are going to take place within a chemical reaction that we can study. And so we're going to see kind of like first a chart here that just looks at different substances, that they have characteristic specific heats. And a specific heat is a measure of how much heat it takes to raise a substance's temperature, 1 gram of a substance by 1 degree C. So if you notice the units on specific heats, that's the CS value here is our specific heat. And that's the amount of heat it takes to raise 1 gram of a substance by 1 Kelvin or 1 degree C. And so we're talking about changing an object's temperature. So imagine we go from 25 degrees C to 26 degrees C. And if we think about converting 25 to Kelvin, that would be 298 Kelvin. I can write today. 298 Kelvin. 26 in Kelvin's 299 Kelvin. So if we go up by 1 degree C, we're going up by 1 Kelvin. So we can look at all these units here that are joules per gram Kelvin and see that those would be equal to the same units in joules per gram degree C, because to go up by 1 Kelvin is the exact same increase in temperature in degree C. So that this works here because delta T in Kelvin is equal to the delta T in degree C. Now I'm leading with this here because we see a lot of conversion errors made just from this fact alone. So when you think about going from 25 to 26 goes up by 1 Kelvin or 1 degree C, sometimes we see double conversions of temperature within this chapter. So when we look at some problems, I'll try to make sure I point out a few cases where we mistakenly sometimes double convert into Kelvin. And so just know that in this equation here, we're thinking how much heat is required to raise a given mass by its specific heat a certain temperature. And so Q is equal to MCS delta T is telling us how much heat would be required to raise a certain mass of substance by a certain amount of temperature. Let's look at some different substances specific heats. Water liquid kind of stands out because it's probably the most commonly used number on this chart that we use a lot. And if we're actually more precise here, it would be 4.184 joules per gram Kelvin. The reason why I point that out is you might know the conversion between calories and joules, if you happen to have used those units before, is that 1 calorie is equal to 4.184 joules. And so the conversion factor between calorie and joules is given or is found within the specific heat of water, and that's for a good reason. It turns out the calorie scale, we don't talk about calories too much in this class in terms of the unit, but we use those a lot in our everyday lingo. Just a quick little sidetrack would be if you look at the calorie content of food, that's actually kilocalories. So sometimes we call that a capital C calorie. If you look on your food labels, it all has a capital C for calorie. That's really 1,000 calories. So when you see something has 100 calories in a food item, it's really 100 kilocalories is the actual content of the food. But then the calorie unit was defined precisely by the amount of heat that's required to raise 1 gram of water precisely by 1 degree C. And so the calorie scale is actually defined off of the specific heat of water. And so we deal more with joules in this class. And there's a conversion, I don't know if I mentioned this before, but the 1 joule in terms of fundamental SI units is equal to 1 kilogram meter squared per second squared. And I just like to throw this back to the idea that the joule is the unit that connects to fundamental SI units of mass, length, and distance, and their distance and speed, and their SI units of kilograms, meters, and seconds. Not a big detail. This is usually a given value on a test on the equation sheet, but I just want to make sure I connect that this is the joule, the SI unit. And then the calorie here would be equal to 4.184 joules. And again, we're not going to deal too much with the calorie. You don't have to memorize the conversion factor, but you may have seen that number before. And so for water, what it's saying is if we want to raise water's heat by degree C, it takes a little over 4 joules of heat for that substance to absorb. If we had a different substance like solid iron, now we do heat up solid iron a fair bit, maybe a cast iron skillet is where we do this. And so you can imagine that if you had if you use cast iron, it's a heavy skillet, that it takes it probably a lot less time to heat up than in an equivalent mass of water. So if you had a pot of water, it takes water, 10 minutes on the stove to heat up depending on your stove. and how much water, et cetera. But if you had about the same amount of mass of water versus iron, the iron heats up faster because it has a lower specific heat. And so it takes less heat, it has to absorb less heat in order for it to change its temperature compared to water. Water takes about 10 times as much heat, so it takes it a fair bit longer to warm up to the same temperature. And you can see some other substances here have different and characteristic specific heat. So specific heat's a characteristic property of a substance. Let's look at a problem. It says a key problem to wrap up. I guess maybe I thought we were going to wrap up class with this last time, but this is a good problem maybe to start the topic with here. Is, given the specific heat of water is 4.184 joules per gram Kelvin. Sometimes you see the joules per gram Kelvin given this way. Sometimes you see it just given this way here. Either way, it's just the units, joules in the top and grams in Kelvin in the denominator. So how much heat must be absorbed to increase a kilogram of water from 20 degrees to 95 degrees? And so our thought here is just a plug and chug into the Q is equal to MCS delta T equation. And so our CS is in joules per gram Kelvin, so I'm going to convert this mass here to grams. So I have 1,000 grams. If I'm tracking sig figs, that's 1,000 grams with 3 sig figs times my specific heat, 4.184 joules per gram Kelvin. And then I can do this conversion a couple different ways. I'm going to do it this way here. 95 degrees C, so this is my final temperature. This is my initial temperature. And so my delta is just the final minus the initial temperature. So my delta T is just the T final minus the T initial. So 95 degrees minus 20 degrees, those being Celsius. And I'm going to go ahead and just cancel those units out because they're synonymous with each other. I just need to get used to doing that. Now, to make sure I see why this works, and the one thing that sometimes happens is you do this difference here in degrees C, that's 75 degrees C is the difference. So sometimes I see 75 degrees C converted to Kelvin here. That's not correct, is it? So if I convert 75 degrees here, like it's a temperature measurement, and I convert that to Kelvin, I'm making a fundamental mistake, because if I want to convert to Kelvin, think about converting 95 to Kelvin, think about converting 20 to Kelvin, then take the difference. And let's do that real quick just to make sure we see. So if I convert 95 to Kelvin, so if you remember, the temperature in Kelvin is just the temperature in degrees C plus 273.15. And so I'm going to lose the 0.15 with the sig figs here. So if I take 95 plus 273, I get 368 Kelvin. If I convert 20 degrees to Kelvin, I should get 20 plus 273, which is 293 Kelvin. And so then 368 minus 293 is 75. So the same number of degrees C is equal to the same number of Kelvin. Now this doesn't mean that if you had a temperature of an object that was 75 degrees C, that the object's temperature would be 75 Kelvin. No, the object's temperature, if it were 75 degrees C, would still be 75 plus 273. But if you're saying you had something at 20 and you increased it to 95 such that the delta T was 75 degrees, that if you convert 20 and 95 to Kelvin, take the delta, you also get the same number, 75 degrees C. So delta T's, change in temperatures in degrees C, are equal to the same magnitude, the same number in Kelvin. And so if you recall, when we talk about temperature scales, I'd pointed out that the temperature scale for Kelvin and degree C both go up by the same amount. So going up by 1 degree C in degree C is the same as going up by 1 Kelvin. Okay. And again, I'm highlighting this because I know this is a calculation error that a lot of times is made on a test. So again, if I write this down here, I go 1,000 times 4.184. Let me make sure I write the grams in again. And so joules per gram Kelvin, that cancels. And then I can either multiply by 75 Kelvin, see it cancels, or just start canceling out my delta T's in degree C and Kelvin and being okay with that, and not double converting or making a mistake of reconverting into Kelvin. And so if we do this math here, so 1,000 times 4.184 times 75, I get 313,000 314,000. So this equals 314, rounding to 3 sig figs joules. So I might convert this to kilojoules. So 1,000 joules is a kilojoule. So this would be 314 kilojoules to raise 1 kilogram of water from 20 degrees to 95 degrees. Okay, so to warm an object up, it has to absorb heat. So this is an endothermic process. Heat has to be absorbed by the water for it to increase its heat here. And there's no actual change taking place in the water. We're not changing any bonds in this process. We're just literally increasing the temperature, seeing how much heat's associated with that. Now, one of the things that we can do here in chapter 5 is we can try to track the temperature change of water if we start throwing like reactants into the water that are reacting, and we can start to see how's water's temperature going up and down. What can that tell us about a reaction's temperature change? And so one of those type of problems is just if we wanted to determine or just relate specific heats to each other, we can imagine taking a hot piece of iron and then putting that into water. And so we can have just the simple reaction being something hot going into something cold and their temperatures equilibrating. And so this example here, we're putting 10-gram piece of iron into 100, so the iron, 10-gram piece of it's at 100 degrees. And the way you might do that, you might have a test tube. You might heat up the iron in the test tube in like a water bath. So the water bath's at about 100 degrees C. So you get your hot piece of iron, and then you pour it, you dump it into another container. We call it an isolated system. Just imagine a Stanley or a thermos or something. So we put it into a thermos with 25-degree water in it, and then we put a thermometer probe into that solution and try to see what the final temperature is. And so we're asked here to try to calculate the final temperature of the water and the iron once they thermally equilibrate, meaning they reach the same temperature. So thermal equilibration would just mean that they have the same final temperature. So they have the same final temperature as each other. So the water's 25 degrees, the iron's 100 degrees, so somewhere in the middle they should meet. And so it's not gonna be necessarily right in the middle, but it should be probably, if you think about the relative specific heats, the specific heat of water takes a lot of heat to raise water's temperature. It didn't take a lot of heat for iron to raise its temperature. So iron doesn't have much heat to lose. Water takes a lot of heat for it to change its temperature. So we're probably gonna predict that this TF should be probably just slightly above 25 degrees C, but probably not that much higher because the initial temperature of water is 25 degrees C. We're not gonna expect it to be below 25. We're not gonna take something hot, something 25 degrees C and see the temperature for them both equilibrate to a lower temperature. So we should end up a little bit higher than the temperature of water. And the whole idea here is kind of a system versus surroundings that we have, you know, kind of or maybe a Q hot versus a Q cold situation where we have a hot object that's looking to lose heat and we have a cold object looking to gain heat. And the way I can mathematically think how this works is just with a simple minus sign. And if you think of how math works, you can put the minus sign on either side. You know, like if you had, we could write minus Q hot is equal to Q cold, or Q hot is equal to minus Q cold. I'm not implying necessarily that either side of this equation is negative or positive. Where I put the negative sign, I'm just saying that the two heats are opposite of each other. So the iron has heat to lose, the water is going to gain the heat that's lost. There's nowhere else for that heat to go but into the water. And so the idea here is just you have the iron hot, the water down here in terms of its heat, so water's gonna increase and the iron's gonna drop in terms of its temperatures, maybe a schematic of what's gonna happen. And then if this is, you know, we're thinking this is our iron because it's the hotter object, this is our water, this is our colder object, and they're both pure substances. To go back to specific heat for a minute, the idea of specific heat, we can have a specific heat for a pure substance. When we have just pure water, pure iron, we can have for that specific substance, the heat for 1 gram of that substance to raise its temperature by 1 degree C. And so from the table on the opening slide, we saw that the CS for iron was 0.45 joules per gram Kelvin. So I can be thinking for iron that I can have its Q is equal to MCS delta T. So the Q was equal to MCS delta T, but this is for the iron part of the problem, and that's going to equal the negative Q is equal to MCS delta T for water. So the Q for water is the MCS delta T, but for the water. And then I just have to have this minus sign here because, again, the heat being lost by the iron is being gained by the water. I could divide both sides by -1 if I wanted to put the minus sign on the other side. It does not matter what side of the equation I write the minus sign. And so the only thing that really matters then is that I write the proper mass in for iron versus water and the proper specific heat. So for iron, we're just going back to the table 5.2. That's where we're getting the CS is equal to 0.45 joules per gram Kelvin. And so what I can write for iron is we have 10 grams of iron, the specific heat. I usually have a lot of different times I mentioned this, but the most likely cause of a mistake in almost any problem in math, physics, and well, maybe not math, but in physics and chemistry is not showing units. So if you get in the habit of not writing in your units, I would try to change that habit because you will catch a lot of mistakes and you will also then probably figure out how to solve some problems you don't know how to solve just by looking at the units and trying to make sure that you get the units to work. And so a delta T is our T final, which we don't know. Our T initial, we do know for iron was 100 degrees C. So this is what we're going to solve for here eventually. That's what we want to know is what final temperature does the iron equilibrate to? And then we're going to set that equal to that for water, the negative mass of water. We had 100 grams of water given to us in the problem, 4.184 joules per gram Kelvin. And then it's TF. We don't know. It's T initial, 25 degrees C. And so now, occasionally we arrive at problems that just become mathematically what they are, just slightly tricky math problems to solve. Let's look at the units real quick. Our delta T is going to take care of the Kelvin. And so then we're going to, the joules themselves are going to end up dividing out. So I think our units are going to fall into place. So I think unit-wise, we put everything in correctly. So what we have to do now is just try to solve an algebra problem. So now we just have to do the kind of algebraic factoring into the equation and rearranging. And so 10 times 0.45 is 4.5. So I'd have 4.5 times TF, and then factoring that in, times minus 4.5 times 100. I don't know why I'm doing this in the calculator. That'll be minus 450. And I can even think of keeping my units here. I'm going to keep everything in degree C. Again, remember, degree C and Kelvin are fine here, so I don't need to convert anything to Kelvin. And so then 100 times 4.184 is 418.4. So I do this math here. Again, not sure why I'm putting that into a calculator. But so I'm going to have negative 418.4 times TF. Then I have to factor that into times negative 25 degrees C. So negative 418.4 times negative 25 is 10,460. So I'm just doing this math here. So just to make sure you see, like I'm just doing that. Negative 100 times 4.184, then times TF, and then negative 100 times 4.184 times negative 25 degrees. So we get that plus sign here, just from the negative here and the negative there. Okay, and so I keep rearranging. And so then, perhaps I subtract, or I guess I would add 450 to both sides. So let's do that. So let's add 450 to get rid of this here. So I have to add 450 degrees C over here. And then I need to add 418.4 times TF to both sides to get rid of that over here. So I add 418.4 times TF to both sides. And so that should be 422.9 times TF is equal to plus 10,460 plus 450. And if we're still tracking some units, I do have joules here. I could have kept the joules there and they'll cancel into each other when I do the final step, and I'm gonna keep that degree C. So the way the units work out here is my final temperature should be equal to that 10,910 divided by 422.9, and I get 25.80. We could go back and think about sig figs. I would rather not, but it's a fun sig fig problem if you think about it, because there's like 50 million subtractions and multiplications. But I think we're good with 4 sig figs here. So 25.80 degrees C. Now, a couple thoughts. One, it's really easy to make a mistake on this math here. And really, like, I don't like this math problem for the math part of it. I do like the thought of it, though, for the hot thing into the cold thing. The cold thing has to get a little hotter, and the hot thing has to get a lot colder in terms of its temperature. So the iron goes from 100 degrees C all the way down to 25.8 degrees because it didn't take that much heat for iron to raise its temperature. Remember, its specific heat is 1/10 of that of water approximately, so it doesn't absorb that much heat for it to increase its temperature, and there is only 10% of the mass compared to the water and iron. So we put a lot of something that didn't have really that much heat, so it makes sense that the iron's going to lose a lot of heat, change its temperature by a fair bit, and water just marginally goes up by 0.8 of a degree here by adding that hot piece of iron to it. But then in terms of the math, like if you do see a problem like this on a test, you can sometimes look at the choices if it's multiple choice, or if you get to the very end, if you get to this end step here and you calculate 22.8 degrees C, you can be like, well, that fundamentally does not make sense. There's gonna be a lot of cases when we look at calorimetry problems, if we just fundamentally understand that the temperature should go up or down based on something we know about the problem, we can easily catch a math mistake. Because a lot of this chapter will depend upon us really just like knowing where that one negative sign goes and making sure we understand why it's there so that we don't make that mistake when we see something like this on a test. And so this is how we look at kind of just like comparing specific heats of objects being mixed together. But still, like this, if you ask me, this isn't quite a chemistry example yet because we're not doing a chemical reaction. So why don't we do an example where we look at a chemical reaction occurring inside of something like water, so then we can track the temperature of water or the solution and then try to see what's going on in terms of the enthalpy of the reaction. So let's try to break this down into a couple of steps here. And so this form of calorimetry we often call coffee cup calorimetry because you just literally do the reactions in an insulated cup, which a lot of times in the lab when we do this, we just take 2 styrofoam cups, which is a reasonably good insulated cup. Like I mentioned earlier, a Stanley would work great. You know, something that's a really good insulated cup is what you want to have. We're not really going to seal this in terms of an open versus closed system. Like you see the cork on here, and you see like a thermometer probe that has like a hole drilled through it. This isn't going to perfectly seal in the mixture. The cork is there just to kind of keep the insulation going. You know, so it's just kind of like a lid to keep everything intact. But the pressure is not held constant here. So if the pressure was going to increase, if we're generating a gas, it's just going to escape through the container. So this is still, even though it looks sealed in, it's still constant pressure calorimetry, meaning that the heat change is equal exactly to the delta H. So the heat change that we can study in this solution here is going to be precisely equal to the enthalpy change of the reaction. So this whole idea here is that the heat of the reaction at constant pressure is telling us something about delta H, so that we can solve for the enthalpy change through this type of system. And so what goes on in this case here is we put water in, we track the temperature of water. When you do this in the lab, it becomes a little bit tricky and complicated to actually know the temperature of the water because the temperature reading usually fluctuates a little bit. But in an example that we give you, it's always very easy because we can just say that hypothetically you put 2 grams of ammonium nitrite, we're going to have that solid at some temperature. It's easy to say in a problem it's 25 degrees C. It's a little harder in the lab to know its temperature is 25 degrees C. But then we're going to add that to a certain amount of water. And the water is usually given to us in grams because we're going to relate joules heat is equal to MTS delta T. So we really need masses here, not volumes. I could give you a volume of water and a density, and it just adds a little bit of nuance to the problem, but we really need to know the mass of water. So we take a certain mass of compound, we're going to add that to water inside of a coffee cup calorimeter, and the temperature of the solid and water are initially known to be 25 degrees C, because that's good to know, because like we want to know initially they're at 25 degrees C, and then something's going to happen, that reaction that the ammonium compound should dissolve in water. We learned all ammonium salts are water soluble. So we should have the dissolution reaction take place where we have the ammonium nitrite added to water as a solid, where it ionizes into NH4 plus, aqueous, and then NO2 minus, aqueous. And so that's the reaction that's going on. We can understand that from chapter 4. And so when we add this to the water, the temperature of the solution, we made a solution, so it's not just the water, but the entire solution's temperature lowers to 22.24 degrees C once the solid fully dissolves. So you can imagine we add the solid, we stir it, maybe a stir motor to help it, and then we kind of just look at the temperature and wait to see when it kind of like levels off. It levels off at 22.24 degrees. So the first question would be, was heat given off by this reaction or was heat absorbed by this reaction? What do you guys think? So the reaction, in terms of the reaction, did it absorb heat or did it give heat off? Who says absorb? Who says the reaction gave heat off? See a lot more hands for gives off, but it's actually not gives off. If the reaction gave heat off, it would heat up the water. So if the reaction loses heat, that heat goes into the water's temperature goes up. So we have to think the reaction is not what we're tracking the temperature of, it's the solution of the surroundings. And so when I'm thinking of the Q reaction versus the surroundings, I always have this fundamental relationship that in order for a reaction here to gain heat, if we're gonna gain heat, absorb heat by a reaction, then that heat has to come from the surroundings, so the surroundings heat has to drop. So the reaction's absorbing heat, that causes the surroundings to lower in temperature because they lost heat. And so if we take heat away from the water, then we're lowering its temperature. If we see the temperature of the water is lowering, we know that its heat's being lost to the reaction as it's taking place. So the reaction here on the reaction side is endothermic. Okay, so the reaction's absorbing heat, where's it coming from? It's coming from that water. That's why the water temperature lowered. So we have to think that the water, the solution is over here. The solution is the surroundings. So the solution that this compound is dissolving into, that water, that is directly an observation of the surroundings of the reaction. Think of it like this. If this is in a cup if we just do this in a beaker, we did this the other day, where we took a similar compound, ammonium nitrate, that was also endothermic, we added it to water and the temperature dropped and it felt cold. Because when I touch the flask, I'm part of the surroundings, and so I feel cold because it's taking my heat away from me, so I feel that cold temperature. If I feel heat going into my hand, then that means that the substance had to be hot, and if it was hot, had to mean that the reaction gave heat off. It's giving that heat into me when I touch it by touching the surroundings. Okay, so this reaction here is endothermic, and then can I calculate the heat of the reaction that occurred inside the coffee cup? And so that's usually the next step, is if we can quantify the Q reaction. So the way I can quantify the aspects of the heat of the reaction here is to make that relationship that it's a negative Q of the solution. It's the opposite of the heat change of the solution. The solution is what I'm monitoring the temperature of. And so the solution is mostly pure water. So what I can write for the solution is I can write it has an MCS delta T, just like water does or any other substance. And so I can write for the solution, I have the M solution times the CS of the solution times the delta T of the solution. Now, we're often told here to assume that right here. So assume the specific heat of the solution is 4.184 joules per gram Kelvin, basically that of water. So the solution is, 2 grams ammonium nitrite in the ions of that compound and 50 grams of water. So, we're like 96% water, something like that. So we're mostly water. Not totally water, so this is an assumption that's not entirely going to be 100% accurate, but it's the way we're going to look at most problems. So most problems, you look at a relatively dilute solution so that the specific heat of the solution could be assumed to be that of water. And so then when I throw into here is the mass of the solution. What's the solution mass? It's the entire mass of the 52 grams. So if we're just thinking here, the solution is the compound and the water, so I have negative 52.0 grams. The specific heat, 4.184 joules per gram Kelvin. And then the delta T is the final minus the initial. Let me write this over here. So the delta T would just be the final temperature, 22.24 degrees C, minus the initial temperature, 25.00 degrees C. So that's negative 2.76 degrees C. So two things. One, the negative sign here is only coming from the idea that the reaction's the opposite of the surroundings is the solution. So fundamentally, Q reaction, negative Q of its surroundings. And so this negative sign here is coming specifically from any reaction will always be Q reaction, negative Q surroundings. We can only ever track the temperature of the surroundings. It's hard to put a thermometer, I've mentioned this before, it's hard to put a thermometer on the reaction itself, because the reaction itself is the ammonium nitrite that was there versus the solution that is there now. So how do you touch the before and after there? You really can't. The only thing you can do is be in contact with the before and after. And so the before and after is the surroundings. And then the other thing is a delta is always final minus initial. And so if we just remember the final temperature minus the initial, and we just keep the sign, and if you notice, negative 52 times 4.184 times negative 2.76 comes out to be a positive number. So we kind of double check here. We get, as long as we do the math correctly, as long as we put the minus signs in the right place, we get these minus signs to work out that we get back to an endothermic, a positive greater than 0 delta H, or Q reaction. So my Q reaction works out to be negative 52 times 4.184, and then times negative 2.76, and that's 600.5 joules. If I convert that, I think it doesn't say to convert it to kilojoules, so I'll leave this here as the number in joules. So it's 600.5, and I think it should just have 3 sig fig joules. So 52 had 3 sig figs, the 2.76 has 3 sig figs, so we're at about 601 joules here for the heat of the reaction occurring inside of this coffee cup. So that's the Q reaction that's occurring inside that little coffee cup here when 2 grams of compound is reacting or dissolving into 50 grams of water. And so then can we calculate though, this is usually, the question will ask this, and sometimes when you get into examples, when you get into some daily quiz examples or homework examples, a lot of times you may not be asked that middle question of calculate the Q reaction that's occurring inside of the coffee cup. But we have to do this step first. So this becomes almost like a one-step process. And then the second step, and this is what we usually ask for. This is kind of like when we ask you to find an empirical formula, you have to know to get the mole ratio and then find the simplest ratio. So there's a series of steps you have to know to go by in order to solve the problem. Maybe we give you a molar mass to get a molecular formula. You know that's a 2-step process. This problem here becomes kind of a 2-step process of find the heat that's that within that little coffee cup example, find the heat of that reaction, and then let's try to think like per mole of the substance. Yes?
So if you were doing the heat surroundings to that sign, why did we include the 2 grams of ammonium nitrate into the grams?
Yeah, so what we're trying to relate to is the entire solution. Now this is kind of weird, but if you imagine the reaction, the idea of the reaction absorbs the heat. Like in order for the ions to break apart, that there's just a heat change that's going to take place. Now there's a certain mass of the actual compound itself. Like the compound had heat just by virtue of its own temperature. And so the compound itself has a specific heat, meaning that once the reaction needs to absorb heat, it can take the heat from the substance itself, the heat that the molecules have just by virtue of whatever temperature they're at. And so the reason why we're kind of relating the Q reaction to the solution is that the solution's the entire thing that had a certain temperature that's then changing by virtue of the mass of the substance, the specific heat, and then the nature of the reaction that's going on in it. And then I also like to think, since we're writing Q reaction versus solution, I use the mass of the solution, and so that the mass of the solution has both things there. So it's just kind of like thinking, well, what is the solution? It's the solute and the solvent here. So yeah, good question on whether or not you should include just the mass of water or the mass of both things. I say both things because you still have the mass of the reactant of the ammonium nitrite that can have a certain heat, so we include it in the mass. But so then oftentimes we want to know one of two things. Either we want to know the delta H of this reaction here, so like when I kind of like have 1 mole of ammonium nitrite dissolving, what's the delta H of that reaction? Or another thing we tend to ask is what's the enthalpy of solution of the compound in units kJs per mole? If you think about it, the enthalpy of solution is about 600.5 joules per 2 grams. If you think of the ratio, we have 2 grams of compound. So if I'm thinking of my delta H, and let's say we call this delta H solution, because it says, what's the delta H's solution of the compound in kJs per mole? And let me make sure I'm clearly writing out SOLN. So the delta H's solution in kJs per mole. I would get there by kind of recognizing that my 600.5 joules, that heat that was given off was per quantity of the reaction that occurred in the coffee cup. So I have to then think that this heat here, I need to divide this by whatever the limiting reactant was in that reaction. So I have to kind of go back to this reaction here and realize, oh, that was 2 grams going in. Like what limits the heat here is how much of that compound dissolves in water. And so what I divide by here is the 2 grams of compound, and just kind of see that heat's a ratio to the compound. So if I had 4 grams that could dissolve, now sometimes you hit a solubility limit. You fundamentally may not be able to physically dissolve 4 grams. But if I could have 50 grams of water and add 4 grams, you would probably imagine the temperature would lower even more. If I could add 8 grams, the temperature should lower even more. So the magnitude of the delta T should be related to how much compound we put into the water. And so then, so we take the heat per gram, and then all I need to do is convert to moles. We're given the molar mass here in the problem, 64.05 grams per mole. And this becomes a relatively straightforward gram to mole conversion. So, but the tricky part is seeing that the 600 grams is the heat that was changed by specifically 2 grams of that reactant in the calorimeter. So the enthalpy of solution of the compound, the heat per 2 grams of the compound in the calorimeter. Then I use the molar mass per mole of NH4NO2. So 600.5 divided by 2, and then times 64.05. And then I'm going to convert this to kilojoules, so 1,000 joules per kilojoule. And so kJs, not just kJs, but kJs per mole. So joules canceled, and I have kJs per mole. Okay, so that's how we calculate enthalpy of solution in units kJs per mole. And that's usually what we'd want to know. It's like, if I could put a whole mole of the compound into water, that would be ideal. So if I could have a big enough calorimeter that I could put enough compound, if I could put 64.05 grams of the compound into enough water that it would dissolve into and track the delta T there, then my Q reaction would come out to be delta H. Because really what you want to find here is delta H in like units kJs per mole. Not usually just in the quantity of the reaction that occurred inside the calorimeter, but relate the quantity in the calorimeter to how much the reaction took place and just convert to moles. And then what about the balanced reaction? What about the balanced chemical equation? Well, balanced reaction delta H is if I say, what's the delta H of this reaction? Remember how we assume that the coefficients are moles in the reaction as it's written? So if we're assuming that the coefficient is a reaction, our delta H, sometimes I use this symbol here, not, just to try to indicate the delta H of a standard reaction. You'll see a lot of different types of delta H's. You'll see delta H's that are a property of a solution, like in kJs per mole. A delta H naught, to me, this is telling us this is for the reaction. This is for the reaction right there, for that balanced reaction. So for that balanced equation there, if I'm calculating the delta H of reaction, I know the delta H of solution is 19.2 kJs per mole. And this is as simple as recognizing that there's 1 mole of the ammonium nitrate or ammonium nitrite in that reaction. So 19.2 kJs per mole of ammonium nitrite, there's 1 mole of that in the balanced equation, so it just works out to be 19.2 kJs. So do you remember how if you double the coefficients in a reaction, you double the magnitude of delta H? So if we had 2 moles of ammonium nitrite going to 2 moles of ammonium, 2 moles of nitrite, then it would have been 19.2 times 2. And so you can kind of see how some different delta H's of reactions can be determined. So you just look at the coefficient here as a 1, And so that's how you multiply this by 1. So it's a really simple conversion for this problem. I just wanted to kind of relate the ideas of the heat occurring inside the cup to the heat per mole to maybe even the heat of a balanced chemical equation. Now this form here, I'm going to briefly talk about this because we rarely test this. So this concept here, this form of calorimetry at constant volume, this is rarely tested in this class. And I don't want to spend too much time on a topic that we really don't put on the test, but I just want to mention a couple of details here. A form of calorimetry called bomb calorimetry is where you seal a reaction in a container, and then the container cannot change volume. Therefore, it's not at a constant pressure anymore. So in this container here, you have, and my students were actually just doing this in physical chemistry lab yesterday. So if you want to see this technique, I recommend you become a chemistry major and take my upper level physical chemistry lab class where you get to do this experiment. But you put a substance in a container, it does a combustion reaction. Combustion reactions are usually exo or endothermic. Exothermic, they give off a lot of heat. And so the reaction occurring inside of here is always going to be exothermic by the nature of the type of reactants you put inside of this calorimeter. So you put a compound like heptane. Heptane should burn, it's a hydrocarbon, and it should burn with a flame and produce that heat. That's why we're calling it exothermic. And then this form of calorimetry here, we're tracking the temperature of the calorimeter going up. So we start with a cold calorimeter, the temperature increases as that combustion reaction takes place. So what happens is this container becomes hot, the hot container is in a water bath, the water temperature goes up. And so we end up relating the Q reaction here to kind of like we did before, the surroundings, where the surroundings is the entire calorimeter. And then the calorimeter has just a single heat capacity value that we call Ccal, and we multiply that by delta T. And so if we look at the problem, we have a certain mass of compound completely combusted in a calorimeter where we know the entire heat capacity is units kJs per Kelvin. Notice no gram unit because that's not a specific heat. But I think at this point here, I'll just say that when you see this problem here, you're just literally multiplying this number here by the delta T in the calorimeter, and then you're kind of taking that Q reaction just like we did in the previous example. And so I think I'll go trim this off the homework set just so that we're not spending too much time on this problem in the homework. You'll see some of these problems on the quizzes. It's really hard for me to label all the quizzes, but I would probably not spend a lot of time on the bomb calorimeter examples. They are actually very easy to solve in my opinion. I think they're a little bit easier than the previous form, but the previous form you do in lab, and it's a little bit more common of a problem for general chemistry class. But this is just showing you at constant volume how you can do a different type of calorimetry and study reactions generally in the form that are exothermic. And so I think we'll just kind of move off this topic and kind of head into the next topic. But so bomb calorimetry, no, we can relate the heat changes in this form of calorimetry, but we rarely test it, so we're not going to spend too much time dwelling on this example here. The only thing that I think is worth pointing out is that this technique here is used to determine enthalpies of combustions of compounds. And then from an enthalpy of combustion, we'll see later, we can tabulate things we call enthalpies of formation. So one of our topics soon we'll talk about is enthalpies of formation. You might remember this from high school. If you remember going to an appendix and looking up a delta H of a substance so you can sum up the products minus the reactants, this is the fundamental experiment that's done to determine those values that are tabulated in appendices or in online indexes. Okay, so a quick summary here would be that our Q reaction. This is just the idea. Q reaction is negative Q of the surroundings. And this, all the way back to like the early part of chapter 5, was kind of like our main idea, is that you can think of the surroundings, you can think of your reaction, they're just oppositely related to each other. So if a reaction's losing heat, it's going to the surroundings. If a reaction's absorbing heat, it's coming from the surroundings. And so you can relate the reaction's heat change to the surroundings heat change in calorimetry. So in our coffee cup calorimetry, heat was absorbed by or released by a certain reaction into the solution it's taking place in. If heat is released, the temperature of the solution should go up. If heat's absorbed by the reaction, the temperature should go down inside that calorimeter. And so we have some equations that emerge: Q reactions, negative Q solution, negative M solution, CS solution, delta T solution. And the Q reaction is the heat of the reaction occurring. So the Q reaction we first calculate is for the heat inside the specific calorimeter that we were told about and given data for. We then have to relate that into heat per gram or heat per mole or for a balanced reaction. And then we didn't talk too much about the bomb calorimetry examples, but our Q cal here was our surroundings, so negative C cal times delta T. Okay, so let's get into a few other topics here today in chapter 5. One of these is on Hess's law. Hess's law was one I've kind of already mentioned by name and said it's really just a lesson in the first law of thermodynamics, that if you can add up reactions or physically imagine taking a series of reactants and products and adding them up and canceling out what's on both sides, because if I have a mole of water on this side versus a mole of water on this side, their enthalpies cancel. So whatever you have on both sides of your equation will cancel out, and then you can reduce down to the net change. The net change, if that's a reaction you're looking for, you can determine its delta H. Now this ultimately becomes kind of like a puzzle though. So when we're asked to calculate the delta H for this reaction here, NO plus O goes to NO2. It's a very simple looking reaction that we take NO plus an O atom goes to NO2. If we want to know the delta H of this reaction, that's what we want to know the enthalpy change of, what do? Well, they give us these 3 reactions here that hopefully what we can do through these 3 reactions is try to figure out how do I manipulate these equations here so they add up to balance out to this reaction here. And so if I just add these reactions up as is, I think you can see that that's not going to work. If I add these reactions up as they're written, they don't balance out to NO plus O goes to NO2. So this becomes a puzzle of how do I get this reaction here to add up from these individual reactions here. And so the way I kind of think of doing this is I look for one of the substances, let's say NO, and I see it in one spot here. It's in the first reaction on the reactant side, and that's good. So I'm going to write this first reaction out as is. Everything's a gas, so I'm going to leave off the gas tags. If we have a reaction where some things are gas versus liquid, we have water gas versus water liquid, I might have to pay a little bit more attention to physical states. But if you look, everything in this problem is a gas. So I'm going to neglect writing gas a bunch of times. So the delta H of this reaction is given here as minus 198.9 kilojoules, meaning exothermic reaction. But the whole idea here is if I can add the reactions up, I just sum up their delta H's. What I need to do is I need to figure out, like, how do I get the O atom here is a little bit more complicated. Like I see the O atom here and this reaction here, but it's on the wrong side. So I need that O atom on the reactant side, it's on the product side. So what I need to do to that reaction there is I need to flip it to this direction. But do you notice how there's too many O atoms? So there's too many I only need one O atom. When I add these reactions up, I just want there to be one O atom, but there's 2. So what I need to do to this reaction here is I need to change the coefficients. But let me deal with the flipping the reaction first. So when I flip the reaction, O2 to 2 O's, the forward reaction was 495 kilojoules. What happens if you flip a reaction? What do you do to the sign of delta H? You flip it. You just put a negative sign in front. So if it's 495 kilojoules, so O2 to go to 2 O's, so that's actually an interesting reaction. That's breaking the O2 bond in O2 takes 495 kilojoules of energy. And if we then do the opposite reaction, we're putting 2 O atoms together to form the O2, that's minus 495. So we flip a reaction, let's be precise, it's 495.0. But then I need to cut the coefficients in half. So I need to cut these coefficients by half. So to do that, makes the O down to 1, and then a half O2. So if I have the coefficients cut in half, I need to then multiply the reactions delta H by a half. So if I double the coefficients, I double the delta H. If I cut them in half, I cut the delta H in half. So if I do that, this would be equal to minus 247.5 kJs. Okay, and so what do I do with the middle reaction? Because if I add these reactions up right now, as is, I'd have NO plus O3 plus O goes to NO2 plus O2 plus a half O2. That's not the right reaction. That's not the reaction that we want the delta H of. So I need to use this middle reaction here to cancel out my ozone and my O2. So I have O3 here, and it's not in my overall reaction I'm looking for, but it's in this side here, but as a reactant. So what if I flip the middle reaction? So if I take this middle reaction here and I flip it, and I put 3 halves O2 over here, and I put my O3 over here. And my delta H, if I do that, is plus 142.3 kilojoules. Now this is also an interesting reaction because this is the formation of ozone from oxygen reaction. Ozone is, the fancy word for ozone, it's an allotrope of oxygen. It's a different form of the element oxygen. The only other element I think that has common allotropes that might be worth talking about is carbon. Carbon has diamond, graphite as its two most key allotropes, but also has buckyballs, Buckminster fullerene. It also has carbon nanotubes. So there's actually a few different forms of carbon that are interesting. We call those different forms allotropes. So it's forms of the same element, different forms of the same element we call allotropes. And so oxygen to form ozone takes energy. So ozone's higher energy. It's important in the atmosphere. It blocks out UV rays. We'll talk about that a little bit in chapter 6. But O3 is less stable than O2. It takes energy to form it. And so the reason why we have it here, though, is O3 on the reactant product side cancel each other out. So whatever the energy or enthalpy of O3 is in the reactant side is counterbalanced by its enthalpy on the product side. They cancel each other out. I also have the 3/2 O2 over here that's canceled out by those 3/2 O2 over there. So my O2s cancel and my ozone cancels. And so what does that leave behind? It leaves behind NO plus O goes to NO2. So I add these reactions up. So just think about summing up the reactions. What do they sum up to? They sum up to NO plus O goes to NO2. So these problems are a fun puzzle, or depending on an awful puzzle, I guess you might think of it that way. But to me, they're just a puzzle of how do you need to manipulate the equation so they sum up to the desired one. And then the reason why you're doing that is you have to see how do you manipulate your delta H's. Like the middle reaction that I wrote out, we had to flip and cut the coefficients by half. The third reaction I wrote, we had to flip. And when I flipped it, I changed the delta H accordingly. So if you notice, what I'm doing is I'm trying to figure out how do I need to adjust these delta H's in order for those reactions to sum up to the desired reaction. So if I can add the reactions up, I just add up their delta H's. But the delta H's of the reactions I actually summed. So I would take this as negative 198.9 plus negative 247.5, then plus 142.3. And so I get negative 304.1. So the idea is if you can add the reactions up to a new reaction, that new reaction's delta H is just the sum of those reactions' individual delta H's. This is just a much more complicated example of A to B was plus 20, B to C was minus 40, so A to C was minus 20, if you remember that example we did earlier in the class. And so it's just a simple exercise in the first law of thermodynamics through what we call Hess's law. Now, another topic that we'd like to know or try to figure out is how can we come up with data so that, like I mentioned earlier, if you had an appendix of values of enthalpies, the idea would be if you had some random reaction of A to B, well, what if I had a way to look up my product's enthalpy versus my reactant's enthalpy and just look those enthalpies up so I can sum up the products and subtract the reactants? That's where enthalpies of formation come into play. And the idea of enthalpies of formation is you start with a formation reaction where you form a compound from its elements. And so when you think of a formation reaction, you're forming whatever the product is here from its elements, but in whatever their elements' most stable states and forms are at room temperature. So what's the most common form of O2? It's O2. So oxygen here, its formation reaction is defined to be 0 because its formation reaction is what we call an identity reaction. It's just forming itself from itself. There's no enthalpy change there. Now, ozone's formation reaction would be from O2 because the most stable form of oxygen is O2. And so to form ozone comes from O2. So we leave the formation reaction with 1 mole of the compound, and then we actually go with the fraction. So we need 3/2 O2 to balance that out. And so we have 3 O atoms on both sides. And then the delta H there is what we call the formation. The enthalpy of formation of ozone is 142.3 kJs per mole. Now, if you then said, well, what's the delta H of this reaction? It would be 142, positive 142.3 kJs. So the delta H of the reaction comes from writing the product, just 1 mole of it, and then the formation reaction is forming the compound from its elements, but in the elements' most stable states. So let's get back into this topic on Monday and kind of see for a few other substances how we put these together. and then how we put them together to use them for problems like this. This is what we're building towards. Delta H of this reaction, we can use enthalpies of formation. So we'll get into this next week, guys. Have a great weekend.